In this video, we will talk about deductive proof. So basically, we will start with reasoning process. We'll discuss two different types of reasoning, that is inductive approach and deductive approach. And we will also discuss the deductive proof with the example. So reasoning means to derive something. So we will start with some assumption, and through steps, we will try to prove that that assumption is correct or not. So there are two fundamental ways of doing the reasoning. One is forward, another one is backward, or we can say it's inductive reasoning or deductive reasoning. In inductive reasoning, we are trying to develop a theory from the given data. So initially we will observe very limited samples, and we try to say that, okay, whatever assumptions we have made is true for this data. Then we will try to see the pattern at a larger scale. And finally, we can conclude that, okay, it is true for all the data. So that is how inductive reasoning is working. So we are trying to develop theory from the data. The inductive reasoning is exactly reverse approach, where theory is given and we are trying to prove that it is true for any given specific case. In case of inductive reasoning, we have a specific case and we are trying to generalize it. That's called inductive reasoning. Whereas in case of deductive reasoning, we have a generalized form of rules and we are trying to prove the specific case. Consider the example of inductive approach, where we have observation of very limited data. For example, a low-cost airline flight is delayed. Customer might have experienced delay in one or two flights, but based on that limited data, we cannot make a claim that all low-cost flights are delayed. So we have to observe the pattern. If it is repeating or if it is occurring for all the data, then only we can make the claim or we can establish the theory. So consider that another 20 flights from low-cost airlines are delayed. The sample is now bigger. Initially it was that observation was for one or two flight. Now it is for 20 flight. Next it might be for 100 flight. And so that if it is happening, we can say that all low-cost airline always have delays. So this is what the theory. That is what we have generalized from the observations. Consider another example, that dogs A and B have fleas. It doesn't imply all dogs will have flea. We need to observe this pattern at a larger scale. Consider all observed dogs in apartment have fleas. So that might lead that, okay, all the dogs in street or society or in area could have fleas. Elephant depend on water to exist. So that is true for elephant only. To generalize it, we have to observe it at a larger sample. So we have observed that, okay, all observed animals depend on water to exist. So from these two statements, we can generalize it that all biological life on the earth depend on water to exist. So see that how we have moved from specific case to generalized way. That is called inductive approach. In deductive approach, we already have the theories. It is already generalized and we will try to narrow down the scope. Consider the theories that low-cost airlines always have delays, all dogs have fleas, and all biological life depends on the water to exist. So we need to formulate hypothesis based on existing theory. That is, if passenger fly with a low-cost airline, so this is the specific case that any single passenger or couple of passengers are traveling through the low-cost airline, then they will always experience delay. So that later part, conclusion is already proven. We're just establishing the hypothesis for this. All dogs have fleas. That was the generalized rule. From that we have derived the narrow down hypothesis that all pet dogs in my apartment building have fleas. And similarly for the third case, we can say all land mammals depend on water to exist. So from entire biological life, we have reduced its scope to all land mammals. So what we are doing in this approach is basically, we collect the data and we try to test the hypothesis. So we can collect flight data of few low-cost airlines, we can test all dogs in our building for the fleas, or we can study all land mammal species to see if they depend on water or not. To prove that the generalized rule was correct, we will now test this data, collected data, and assume that we are testing it on 100 flights. So if 5 out of 100 flights of low-cost airlines are not delayed, in that case we have to reject the hypothesis, because Our assumption was all low-cost air flights are delayed, but here out of 100, 5 are not delayed, so we cannot make a generalized rule. Assume that we are testing 20 dogs and 10 out of 20 dogs didn't have fleas. So in that case also, we need to reject the hypothesis. Means our assumption was wrong. We cannot make that statement or the generalized theory for that. And if we study all land mammal animals, then all land animal species depend on water. So that assumption is true. It supports our hypothesis because there is no a single animal or single land mammal which can live without water. That means that statement, generalized observation, is true for each and every life which is on land. So this third statement is supported. In that case, we can say the hypothesis is true. Consider the example that we'll try to prove using deductive proof. So if x is greater than or equal to 4, then 2 power x is greater than or equal to x square. In if the rules, the left hand part is known as a hypothesis and right hand part is called conclusion. So conclusion must be true when hypothesis is hold. Okay? If hypothesis itself is false, then conclusion can take any random value. We are not worried about it. But whenever hypothesis is true, the generalized case, our right hand side of this rule must be true. So let us see. If we check the hypothesis, our hypothesis is what? That x should be greater than or equal to 4. So if I take x is equal to 2, then 2 is greater than or equal to 4 condition would be false. That means our hypothesis itself is true. False. We are right now testing the left hand side or the hypothesis part. If I take x is equal to 3, then 3 greater than or equal to 4 is again false. For these two values of hypothesis, if my conclusion is false, then also I am not worried. Okay, our theory, we cannot say that our theory is wrong because hypothesis itself is wrong. If I take x is equal to 4, then 4 greater than or equal to 4. So hypothesis is true. If I take any value greater than 4, then hypothesis will be always true. So for this value, 4, 5, 6 up to infinity, conclusion must be true. Then only I can make the given statement. But if for x is equal to 2 or 3, if our conclusion is wrong, then we don't have to worry. Okay? Still our rule would be true because we have already given the boundary condition that it is true for x greater than or equal to 4 only. Let us now check the validity of the conclusion, that is 2 power x greater than or equal to x square. For x is equal to 2, it would be 2 square greater than or equal to 2 square. So 4 greater than or equal to 4. So conclusion is also true in this case. You see that our hypothesis is false because x is 2. But conclusion is still true. If we take x is equal to 3, then this would be 2 power 3 greater than or equal to 3 square. That implies 8 greater than or equal to 9. So conclusion is false. Right? Because 8 is not greater than or equal to 9. So here hypothesis is itself false. So we don't have to worry even conclusion is false. So these two results we don't have to consider in either way. For x is equal to 4, 2 power 4 greater than or equal to 4 square, that is true. For x is equal to 5, 2 power 5 greater than or equal to 5, that is true. Okay, so see that for 4, 5 it is true. But we have not tested it for all the values of x. See, just like a conclusion, in step number 1 and 2, value is changing, right? So there might be a possibility that for some x conclusion might be false. If it is so, we cannot make the generalized claim that for x greater than or equal to 4, 2 power x greater than or equal to x square. So we have to prove it mathematically that for any value of x now, conclusion will be hold. So for 6, it is true. Now we will try that it is for any value of x, it will be true. So look at carefully. As x is increased by 1, then left hand side part of conclusion, that is 2 power x, it is increased by factor of 2. So in first case when x is 2, that left hand side part of conclusion would be 4. For x is equal to 3, it is 8. For x is equal to 4, it is 16. For x is equal to 5, it is 32. For x is equal to 6, it is 64. So it is getting multiplied by 2. Whenever we increment x by 1, then left hand side part of conclusion is increased by factor of 2. And right hand side of conclusion increases by the ratio of x plus 1 divided by x whole square. Right? So that is the fixed ratio. You can see that for all the increments on right hand side of the conclusion. For example, if x is 4, then right hand side ratio would be x plus 1 divided by x, that is 4 plus 1 by 4 whole square, that is 25 by 16, it is 1.56 times. For x is equal to 5, the ratio is 1.44. For x is equal to 6, the ratio is 1.36. So as x is increasing, the ratio is decreasing. So if we observe, for x is equal to 7, this ratio would be even smaller, right? For x is equal to 8, it would be even smaller. So this is definitely less than 2 in all the step, and it is going to be down and down. Whereas on left hand side of the conclusion is incrementing by the constant factor of 2. So it's very obvious that for any value after x greater than or equal to 4, the left hand side of the conclusion will be always greater than or equal to right hand side of the conclusion. And from that we can say that it is proved that if x is greater than or equal to 4, then 2 power x would be definitely greater than or equal to x square. Let us check your learning. Differentiate inductive and deductive reasoning and prove the sum of two consecutive numbers is equivalent to the difference between two consecutive numbers squared. And you have to prove it using deductive reasoning. You can post your answers in comment box, and for any queries you can visit the link given in the description box where you can find answers of all the questions or all the such assignments. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.